In this video, I will talk about the relativistically correct definition for the kinetic energy. We know the rest energy of a single particle, the energy that the particle has just by virtue of having its mass, that rest energy is equal to mc squared. Now, from the definition, we define the kinetic energy of the particle to be the relativistic factor gamma minus 1 mc squared. Now, the relativistic factor gamma can be calculated as 1 minus the speed of the object over the speed of light c, and this squared. And the denominator to the power of 1 over 2, or just the square root of the denominator. Now, you will notice this expression includes the speed of the object. So the kinetic energy does depend on the speed of the object, but it depends on the speed essentially through the relativistic factor gamma. Okay, this is the speed. And once you use the speed to calculate the relativistic factor gamma, then here in this expression, in this part, you just use the speed of light c, which is roughly 3 times 10 to the 8 meters per second. Now, I do want to remind you the kinetic energy is the energy of the motion of the point particle. And of course, since this is the energy of the motion, it makes sense that it depends on the speed of the object, the speed of the particle. Now, this is the rest energy, this is the kinetic energy. So essentially you have 1 times mc squared for the rest energy and gamma minus 1 mc squared. If you add these two, E rest plus E kinetic, since you add mc squared and you subtract mc squared, the sum of those two will just be the factor gamma times mc squared. Now, this is just the sum of the kinetic and the rest energy. Now, this expression is valid for any speed. Okay, whether the object is very slow compared to the speed of light, or whether the object is moving at a speed very close to the speed of light, no matter what the speed is, this is the definition of the kinetic energy. This is always valid. Now, this is in contrast with the approximation of the kinetic energy that we often make, especially in introductory physics, that is only valid for low speeds. So if you take this expression, if I start with that, and I confine myself to speeds that are much less than the speed of light, I will not go over the proof for this, but if I confine myself to speeds much less than the speed of light, and now you may ask, and what is much less than the speed of light? Essentially, if you have a speed that is less than 10% of the speed of light, and that will be 3 times 10 to the 7 meters per second. So for speeds less than 3 times 10 to the 7 meters per second, essentially this can be approximated as 1/2 the mass times the speed squared. Okay, I do want you to remember this here, the 1/2 mv squared, is only an approximation, and it is only valid when the speed is much less than the speed of light. If that assumption is not true, then this is wrong, and you will have to use the definition of the kinetic energy. In those cases, you don't have another option.